Good day, everyone. For this lecture, we're going to talk about 2 to the k factorial design, which is a continuation of our discussion of factorial designs. So let's start with the importance of a 2 to the k factorial design. Okay. What is a 2 to the k factorial design? Okay. It's actually the most important special case of factorial designs, and it basically has k factors, each with only 2 levels. That's the base 2 and the superscript k, or the exponent k. Now, the levels may be quantitative or qualitative, that are considered as high and low. Okay. In the case of quantitative, examples could be 2 temperature levels, or for qualitative levels, you could have, say, for example, different operators. Now, the levels may also be the absence or presence of a factor. And 2 to the k factorial design has 2 to the k combinations per replicate. Now, when is the 2 to the k factorial design usually used? This kind of design is usually used at the early stages of experimental work, when more variables need to be investigated. So to maximize the use of your limited resources, first you may actually want to screen the factors that you would want to include in your experiments. And 2 to the k factorial designs require the smallest number of runs in investigating k factors. Now let's go to the base assumptions in a 2 to the k factorial design. Okay, what are the base assumptions? First, that the relationship between the response and the factor levels is linear. Okay, and this is because there are only 2 factors being investigated. Okay, now it is often reasonable at the start of factor screening to have this assumption. And this assumption can be investigated and remedied if not reasonable. Okay, so let's move on to the meat of the discussion on 2 to the k factorial design. Okay, so let's take a look at this example. Suppose that you want to investigate the effect of the concentration of the reactant and the amount of the catalyst on the conversion or yield in a chemical process. Now, the objective of the experiment is to determine if adjustments to either of these 2 factors would increase the yield. Let the reactant concentration be factor A, and then let the 2 levels of interest be 15% and 25%. The catalyst is denoted as factor B, with a high level of 2 pounds of the catalyst and a low level of only 1 pound. Now, the experiment is replicated 3 times, and therefore there are 12 runs. The order in which the runs are made is random. Therefore, this experiment can be considered a completely randomized experiment. All right, so this table shows you the observed data for the chemical process yield example. So as you can see, to the left of this table, you have the 2 factors and the notations for the different levels. And then, so this basically means that this combination, okay, is the combination with factor A at low level and factor B at low level as well. This combination is with factor A at high level and factor B at low level, etc. Okay, and for these different treatment combinations, you have 4 here. Okay, as you have 2 to the 2. Okay, 2 to the 2 numbers of combinations per replicate. All right. And we have here, as you can see, 3 replicates. Okay, for the first replicate, these are the observations for these combinations. For the second replicate, and then the third replicate. And the last column basically shows you the total of the experiments for each row or for each combination. So 80 is equal to 28 plus 25 plus 27, and so on. And this is a figure, okay, a graphical representation of the observed values of the chemical process yield. Okay, as you can see here, on the x-axis, you have the reactant concentration. On the y-axis, you have the amount of catalyst, which is denoted as factor B. Reactant concentration is denoted as factor A. And the lower left of the square is the point representing low level of factor A, or reactant concentration, and low level of catalyst. Okay, and then this point represents high level of reactant concentration and low level of amount of catalyst. This point represents low level of reactant concentration and high amount of catalyst. And then this one is the level where both, or the combination where both factors are at a high level. And these are the observations for these different combinations, which represent the 3 replicates. And this value here, 80, okay, represented or denoted as parenthesis 1, is basically the sum of the observations at this combination. A here is the sum of the observations at this combination, and so on. Okay. By the way, for this example, as given to you, the high level is 2 pounds of catalyst. The low level is 1 pound of catalyst. For reactant concentration, low level is at 15% and high level is at 25%. Okay, so you will see here the notations 1, A, B, and AB. Okay, so we will clarify that in the next slide. Okay, so a note on notations. By convention, capital letters represent effect of factors or their interactions. So for example, A denotes the effect of factor A, AB denotes the effect of factors A and B. And then lowercase letters are treatment combinations, okay? And the presence of corresponding small letter denotes the high level, while absence means low level. So for example, A denotes the combination with high level of A and low level of B. B denotes the combination with low level of A and high level of B. AB denotes the combination at which both A and B are at high levels. And parenthesis 1 means that factors are all at low level. Okay, so this is the convention. Now, lowercase letters also denote the total of all observations. Okay, total of all observations at all n replicates for the treatment combination. So that's why if we go back to this, okay, 1 here denotes the total of all observations where both A and B are at low levels. Note also that a positive denotes high level, or a plus sign denotes high level, while the minus sign denotes low level. Okay, and now how do we interpret the average effect of a factor in a 2 to the k factorial? Okay, now it is the observed. The average effect is the observed change in response due to a change in the level of the factor of interest, average over the levels of the other factors being investigated in the experiment. All right. So mathematically, this is how we compute for the average main effect of factors in a 2 to the k factorial. Okay, so first, let's look at factor A. The effect of A at low level of B can be obtained by subtracting the total, okay, total observations, okay, at low levels of A and B from the total of the observations where we have a high level of A, okay, and low level of B. divided by the number of replicates. All right? While the effect of A at high level of B can be obtained by subtracting the total of observations of combinations where you have low level of A and high level of B from the total of observations where you have high levels of both A and B, and divide that by n. All right? So the average main effect now of factor A is just equal to, okay, the average of these two. All right? So you have AB minus B plus A minus 1 over there divided by 2n. Okay, so if you simplified, or if you rearrange that, you get this expression. Now for B, similarly, we get this expression here. Now, alternatively, you can also derive the average main effect of A and B using this method. Okay, so here you have the average, okay, average observations at the high level of A minus the average of observations at low level of A. Okay, and this is basically equal to, okay, so these are the this is the sum of the observations at high level of A divided by 2n, okay, to get the average, minus, okay, these are the observations, okay, sum of the observations at low level of A divided by 2n, okay, and we arrive at the same expression as we had before, okay, and the same is true with factor B. Okay. How about the interaction effect in a 2 to the k factorial? We can derive the interaction effect in a 2 to the k factorial by taking the average difference between the effect of A at high level of B and the effect of A at low level of B, or vice versa. Okay, so for example, the average interaction effect in a 2 to the k factorial AB is equal to 1 over 2n times the quantity A minus B minus B. Okay, so this one is the difference between the total observations at both high levels of A and B, and then low level of A. Okay, this one is the difference between observations at high level of A and low level of A and B. Okay, so we get the difference of that and get the average to obtain the expression for the interaction effect in a 2 to the k factorial, which is 1 over 2n times the quantity AB plus 1 minus A minus B. All right. And of course, similarly, we can obtain the interaction effect by getting the difference between the average at average of observations, high levels of A and B and low levels of A and B, okay, minus high level of A plus low level of plus high level of B observations, okay, and we get the same expression. All right, so now let's look at the example that we discussed earlier, okay, the chemical process yield. So remember, these are the observed data for the different treatment combinations. You have 3 replicates and you have the total of the observations here, right? So using the expressions that we derived earlier, okay, also illustrated in Montgomery. Okay, so these are the expressions, okay, that we derive. Now, using these expressions, we can then get the average main effects and the interaction effect. So let's look at the average main effect for factor A. Using this expression, 1 over 2n times the quantity AB plus A minus B minus 1. So 1 over 2 times there are 3 replicates. Okay, your AB is the sum of observations for combination where factor A is high and factor B is also high. So that would be this one. Okay, plus A, high level of A, low level of B. So that would be this. And minus B, high level of B, low level of A, high level of B, low level of A. So that would be 60. And then low level for both factors, that would be 80. So we get 8.33. And we just apply the same, the expressions for B and AB to get these values here, which are -5 and 1.67. Okay, so as you can observe already, the mathematics involved here is elementary. It's just, you just have to do a lot of computations, okay? But remember again that there are a lot of statistical packages that are already made available for these kinds of computations. Okay, but the importance of showing this to you is that you know where the values come from and how they were derived, okay, and why they are derived as such. All right, so now let's look at the values that we obtained. So we have 8.33 for the average main effect of A, -5 for the average main effect of B, and 1.67 for the average interaction effect. Okay, so let's look at this value. It is negative, so it means that if we increase B, which is catalyst, okay, amount of catalyst from low of 1 pound to a high level of 2 pounds, then it results in a decrease in the chemical process yield, okay, because of the negative sign. Okay. Now, if you look at this value, it is small relative to the main effects. Okay. How about for A? As you can see, it's positive, okay, which means that there's a direct relationship, and therefore an increase in A, which is the reactant concentration from low of 15% to a high of 25%, okay, results in an increase in the yield. Okay, so take note that in a 2 to the k factorial design, you should always examine the magnitude and the direction of the factor effects in order to determine which are important. Okay. Now, ANOVA can confirm the interpretation of the importance, but it is best to use it in conjunction with an investigation of the magnitude and direction of the effects, as these are not provided by ANOVA. Okay. Now, here are just time-saving techniques for manual calculation of sum of squares as we now shift to ANOVA, okay? And you know that sum of squares is going to be needed in the ANOVA. So, the contrasts, okay, are important, no? Contrasts are very useful in calculating sum of squares. So, sum of square for A is just equal to this expression. Sum of square of P is equal to this. Sum square of the interaction is equal to this. Okay, so if we go back to the expression for the effects, the main effects and the interaction effect, okay, which can be computed as such, this term here is actually a contrast for A. This one is a contrast for B. And this one is a contrast for AB. So in computing for the sum of squares, okay, we just square these contrasts, okay, and divide them by 4n. All right. So in the case of factor A, you have 50 squared divided by 4 times n. N is the number of replicates, which is 3 in this example. And we get 208.33. And then for B, you have -30 squared divided by 4 times 3 again. We get 75 and so on. Okay. Now, the total sum of squares for a 2 2 to the 2 factorial design can be computed using this familiar equation here. Again, you have the sum of all your square of all your observations minus you have your grand total square divided by 4 times n. And this has a 4 times n minus 1 degrees of freedom. Okay. So to compute for the total sum of squares, we use the said formula and we get 323.00. So this value here was obtained by just getting the sum of the square of each of these observations. And of course, the grand total is equal to 80 plus 100 plus 60 plus 90. And then you square that, okay, divided by 4 times 3 to get 9,075, okay? And we get here sum of square total to be 323. Now, the error sum of squares, okay, for 2 to the 2 factorial design can be obtained by subtracting all the sum of square for the main effects and the interaction from the total sum of squares. Okay, and recall that these are the values of the interaction and the main effects. Okay, we just computed for the sum of square total. Therefore, our sum of square for the error is 31.34. Okay, now summarizing all those values in our the familiar ANOVA table, we have here the sum of squares. Okay, and these are the sources of variation. You have the main effects A and B, interaction AB, you have the error, and then you have your total. Here are the degrees of freedom, okay, and mean square, again, computed by dividing sum of square by degrees of freedom. And then your FQ here is just equal to your mean square for the factor or the interaction divided by your error. So 208.3 divided by 3.92 is 53.15. And these are the corresponding p-values. Okay. And as you can see here, the main effects are significant at 5% significance level as these p-values are below 5%. The interaction effect is not significant, okay, even at 10%. And this confirms the interpretation of the magnitude and direction of factor effects that we just had a few slides back. Okay, now let's, before we proceed, let's look at Yates order. Okay, so the standard order or Yates order using the notation, the familiar notations 1, A, B, and AB is as follows. Along the rows, you have the effects. Okay, so you have the main effects A and B, and then you have interaction AB. And then along the columns, you can see the representation of the combinations. So you have here 1, A, B, and AB, 1 representing low level for both factors, A, high level of factor A, low level of factor B, B, low level of factor A, high level of factor B, and then AB representing high level for both factors. Okay, so these here represent the levels at each combination. So for example, this one represents low level of factor A, low level of factor A, high level of factor A, low level of factor B, low level of factor A, high level of factor B, and then high level for both. And then these are just obtained by multiplying these values here. So -1 times -1, +1, and so on. Okay. Now, you can surmise from this that the contrasts are actually orthogonal. Okay. And this means that 2 to the 2 and all 2 to the k designs are orthogonal. Okay, by the way, so you can see here that the contrast for factor A is simply A plus AB minus 1 minus b. Okay, so let's go back to the expression that we derived earlier. So it's 1 over 2n times ab plus a minus b minus 1. So note that ab and a have positive signs, b and 1 have negative signs. Okay, so let's go back to the Yates order. Okay, both a and b have positive signs, and then 1 and b have negative. Okay, so this can basically help you in setting up the expression for the contrast corresponding to the different effects. Okay, and let's just quickly discuss regression model for 2 to the 2 factorial design. Okay, so the regression equation, okay, for a 2 to the 2 factorial design can be represented as such: y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus epsilon. Okay, where x1 and x2 are coded variables. Okay, all right, so to get the value of x1, this is basically equal to concentration minus the value of your concentration at low, okay, plus the value of your concentration at high divided by 2, all over the value of your concentration at high level minus the value of your concentration at low level divided by 2. Similarly, we can use the equation x2 equals catalyst minus catalyst at low plus catalyst at high divided by 2, all over catalyst at high minus catalyst at low divided by 2. So if we use the values for our example on chemical process yield, remember that the value of concentration at low level is 15% and at high level is 25%. The value of catalyst amount at low level is 1 pound and at high level is 2 pounds. Okay, therefore our expression for x1 is equal to concentration minus 20 over 5. Okay, and for catalyst, it's catalyst minus 1.5 over 0.5. Now, fitting the data, okay, to our regression model, we get the following regression model. Y hat is equal to 27.5 plus 8.33 over 2 times x1 plus negative 5 over 2 times x2. Note that the intercept, okay, is basically the grand average of all observations, okay, all observations. And then the regression coefficients are basically 1/2 of the estimated factor effects. Okay, now this is because the factor effects are estimated based on change in y due to 2 units change in the x's, that is from -1 to +1. Okay, whereas in regression, the coefficients represent the mean change in y related to 1 unit change in x. Okay, so for this example, recall that the average mean effect for factor A is 8.33 and the average mean effect for factor B is -5. And we divide that by 2 for the reason that I just mentioned. Okay, now, of course, we always have to check for model adequacy. Okay, and recall that residuals are the difference between observed and the fitted response values. Okay, at low levels for both reactant concentration and catalyst, that is x1 and x2 are -1. Okay, we would get y hat is equal to 27.5 plus 8.33 over 2 times -1 plus -5 over 2 times -1 is equal to 25.835. Okay, so the residuals are E1 would be equal to 28. So these are the observed values. 28 minus the fitted value, which is 25.835. This is equal to 2.165 and so on. Okay, and if we plot all the residuals, okay, in a normal probability plot, this is what we will get. Okay, for the model that we have just derived. Okay, And you can see that it doesn't seem to be problematic as the residuals lie very close to the normal probability line. And if we look at the residuals versus the predicted yield, okay, we also do not see any significant pattern. Okay, so we conclude that the model could be adequate in explaining the model could be adequate in terms of it being able to meet the assumptions. Okay, and to construct plots using the natural factor levels, okay, we have to go back to the expression for x1 in terms of the natural values, okay, the values of the factors. So we remember that x1 is equal to concentration minus 20 over 5, x2 is equal to catalyst minus 1.5 over 5.5. And remember that your x1 and x2 are coded variables from -1 to +1. So using the values that we have computed so far, okay, we would get y hat is equal to 18.33. Okay, let's go to this line first. Y hat is equal to 27.5 plus the mean effect divided by 2 times the corresponding expression for x1 in terms of the natural factor levels. And then you have the main effect of b divided by 2, and then the corresponding expression of x2 in terms of the natural factor level. Okay, now simplifying this expression, we get 18.33 plus 0.833 concentration minus 5 catalyst. Okay, so then we can now use this equation to fit the value for y given the natural values of concentration and catalyst, which are our factors in this experiment. Okay, now using the said model, okay, we can derive the response, we can construct the response surface as well as the contour plot. Okay, now for this example, you can see here along the y-axis your response variable, the values for your response variable, which is chemical process yield, and then you can see on the x your catalyst amount, and then your y and your z your reactant concentration. Okay, and this is your response surface plot. Okay, on the right, you can see the catalyst amount on the y-axis and the reactant concentration on the x-axis, and these are the constant curves for your response variable chemical process yield. Okay, at different combinations of catalyst amount and reactant concentration. Now, since the model is a first order model, okay, then the response surface, as you can see, is a plane. Okay, and as you can see with the direction, okay, of the plane, the yield increases, okay, as the reactant concentration increases and catalyst amount decreases. Okay, so as you can see here, as we decrease the catalyst amount, okay, the amount of process yield increases. As we increase the reactant concentration, okay, the amount of process yield increases. Okay. Now, this can then be used to determine the direction of potential improvement for this chemical process. Okay. The formal method for interpreting the response surface is the method of steepest ascent. Okay, but we will discuss that later on. Okay, so again, these are figures and tables from Design and Analysis of Experiment by Montgomery. Okay, now we are moving on to 2 to the 3 factorial design. Okay, and now we can see a cube here representing with corners representing the treatment combinations for a 2 to the 3 factorial design. So here you have low level for all 3 factors. Here, conversely, you have high level for all factors as represented by the presence of their lowercase, corresponding lowercase letters, okay, and so on. Okay, and your design matrix could look like this. So for your first run, You have low levels for all factors. Second run, you have high level for factor A, low level for factors B and C. And then for the third run, okay, you have low level of factor A, high level of factor B, low level of factor C, and so on. Now we can extend the label notation introduced under the 2 to the 2 factorial design. And we note here that there are 3 different notations in a 2 to the k factorial design. You have the geometric coding, also known as orthogonal coding or effects coding. And then the lowercase letters to denote treatment combinations. And then, of course, you have the use of 1 and 0 to denote high and low levels, respectively, instead of plus and minus sign. Okay, so these are the lowercase letters. Okay, and then you have the geometric coding, and then you have the use of 1 and zeros. Okay. So now, to estimate the factor effects for a 2 to the 3 factorial design, okay, similarly, we can get the contrast, okay, and divide that by 4 times n, all right? So we basically get the difference between this and this, the sum of observations for this and this, okay? And then you have AB, and then you have AB minus B, okay? AB minus B, all right? You have AC minus C, AC minus C, and you have ABC minus BC, ABC minus BC. Okay, so we're basically getting the difference, the average difference from the points on the high side of factor A and those observations on the low side of factor A. All right, so this plane minus this plane, average difference. Okay, so given those, the corresponding expression for the main effect of factor A is this. And alternatively, okay, we can of course obtain this with another method, as in the 2 to the 2 factorial design. So we get the average for observations where A is at a high level, okay, and subtract the average of observations where A is at a low level. So again, we recall this geometric view, okay. At high level, you have A, okay, AB, AC, and ABC. Okay, so you get the sum of all of those divided by 4 times n minus, okay, the observations on the low side. So you have 1, B, C, and BC divided by 4n, okay, to get the average. And of course, this, if you simplify this, this will just be equal to this here. Okay, and these figures just show the geometric representation of the contrast corresponding to the main effects and interactions in the 2 to the 3 design. So for factor A, you have the positive side, the negative side. For factor B, here is the positive side, and this is the negative side, corresponding to the high level and the low level. For C, and so on. Okay. So we can do the same thing for factor B, factor C to get the following expressions for estimating the average effect of these factors. And then, of course, for the interaction. Okay. So to get the interaction AB, okay, you should get the average difference, okay? So you have high level of P, low level of B, and then you get the difference. So this is the average A effect, okay, at high level of P. This is the average A effect at low level of B, okay, and we get the difference of these two, okay, to get this expression. Therefore, to estimate the interaction effect AB, we can use this expression here. Of course, we can derive the same in using a different method again. So you have, and you can use the geometric representation, no, of the contrast. So you have the positive minus the negative plane and the average of that. So this is the positive plane. So looking at the positive plane, you have 1, C, AB, and ABC. That's why you have these terms here. Negative plane, you have A, AC, B, and BC. So you have these terms here divided by 4n to get the average. All right. So similarly, you can obtain or derive the expressions for the average interaction effect for AC, BC, and ABC. All right. Now, you can actually use this table, okay, to more easily determine the algebraic signs for calculating the effects in the 2 to the 3 factorial design. So here you have your treatment combinations along the rows. You have here 1, A, B, A, B, C, A, C, B, C, and A, B, C. Okay. Okay, so along the columns, you have your factorial effect. So here, you can use these signs for calculating the effect of factor A, factor B, and so on. Okay, and note that in these expressions here, in the previous expressions, the quantities in the expressions in the bracket are actually the contrasts, okay, for the corresponding factor. Okay, and to get the sum of square, it's just equal to the contrast squared divided by 8n. Okay, so for example here, let's look at ABC. Okay, so the positive, the combinations with positive sign are A, B, C, and ABC. Okay, in the previous slide, you have A, B, C, and ABC, and the rest would have negative sign. So to compute for the contrast, okay, you can easily use this table to determine the algebraic signs for the terms. Okay, and then the sum of square can be computed by getting the square of the contrast divided by 8n. And this is for the 2 to the 3 factorial design. Okay, now let's apply the model, okay, to a particular example. This is a nitride etch process example. Okay, so this is the given. A 2 to the 3 factorial design was used to develop a nitride etch process on a single wafer plasma etching tool. The design factors are the gap between the electrodes, the gas flow, okay. C2F6 is used as the reactant gas, and the RF power applied to the cathode. Each factor is run at 2 levels, and the design is replicated twice. Okay. The response variable is the etch rate for silicon nitride in angstroms per meter. Okay. And the etch rate data are shown in the following table, and the design is shown geometrically in the succeeding figure. Okay, so this is the table summarizing the etch rate, the observed etch rate for the different combinations. So here you have the run, and then you have the coded factors. All right, factor A, B, and C. Again, what are A, B, and C? So A is your gap, B is the flow, and then C is your power. Okay, and these are the units of measurement. All right, and these are the factor levels. So low level of A is 0.8, high level is 1.2. Low level of B is 125, high level is 200, and low level of C is 275 watts, and high level is 325 watts. Okay, and these are the coded factors. So minus 1, minus 1, minus 1, this means that all factors are at low levels. 1 means positive 1 means high level of factor A. Negative 1 of B, negative 1 of C, they means that both B and C are at low levels. Thus, the treatment combination notation small a. Okay, and here you have the observed values for replicate 1, and then observed values for replicate 2. All right, and these are the totals, total observations for each treatment combination. Okay, and this is the geometric representation of the experiment. Okay, so you have here gap, okay, factor A. You have here flow as factor B, and you have here power as factor C. And here you have the total observations for each treatment combination. You can also see here the levels, okay, of the 3 factors. All right, so given those data and using the expressions that we derived earlier, we can now compute for the average effect of the factors and the interactions. So for A, we use this expression, B, this expression, and C, this expression. So again, take note that this expression here in the bracket is the contrast for A, and the same is true for B and C and the interactions. Okay, using the values from the given example, we get the following values for the average effect of A, average effect of B, and average effect of C. And so on for the interactions, AB, AC, BC, and ABC. All right, and as you know, to compute for the sum of squares, okay, we just get the contrast, which are in the brackets, okay, and square that and divide that by 4n, okay. Divide that by 8n. Okay, so for example, SSA is equal to negative 813 squared divided by 16. Okay, and that is equal to this value here. So we now have the table here, which is basically the effect estimate summary, okay, for our example. So we have our factors here. These are the effects, okay, and the computed sum of squares, okay. And the percent contribution is basically the sum of square of the factor of interest or the interaction of interest divided by the total sum of square. Okay, so for example, 7.77 here is just 41,310 divided by the sum of all these sum of squares. Okay, now it seems that the largest effect, okay, corresponds to power, which is factor C, with 306.125. Okay, so looking at the effect estimates, this one has the highest magnitude. Okay, and it is positive. It is followed by, in terms of magnitude, it is followed by negative values both for the interaction, okay, interaction AC, okay, and the gap A, factor A. Okay, so that's negative 153.625 and negative 101.625 respectively. Okay, Now, as I mentioned earlier, you can also look at the percent contribution, and this can often be a rough guide to the contribution of a model term. And as you can see here, the largest contribution comes from factor C at 70%, which roughly corresponds to 70% of the total variability, okay, in the response variable comes from or is related to your factor C. And about 17 or 18% is from the interaction of A and C, and then that is gap and power, okay, and then 8% from gap. Okay, now here we can see the ANOVA table for our example. You have here in the first column, as usual, the sources of variation. Factor A, gap, factor B, the gas flow, and factor C, power, and then their interactions, 2 factor interactions and the 3 factor interactions. And then, of course, you have your error and your total variation. And you have here the computed sum of squares, you have the degrees of freedom, and then you have your mean square. And mean square is equal to sum square divided by degree of freedom. F naught, again, is mean square of the factor or interaction divided by the mean square of the error. Now, looking at the p-values, you can see that power C has the lowest p-value, and it's below the significance level of 5%. And you can also see a very low p-value for the interaction AC, gap and power, as well as that of gap. Okay, so which signify that these are the terms that are significant in the model. Okay, therefore, we can have the following regression equation for our example. To fit the value of the response variable, okay, H rate, y hat is equal to beta naught hat plus beta 1 hat times x1 plus beta 3 hat x3 plus beta hat 1 3 x1 x3. So this corresponds to factor A, factor C, and then the combination, the interaction of factors A and C. Okay, again, beta hat naught is equal to the average of all observations. Beta hat 1, okay, is equal to the average effect estimate for factor A divided by 2, okay, times x1, which is a coded variable. And then similarly, beta hat 3 is the effect estimate for factor C, okay, divided by 2. And then you have here the effect estimate for the interaction of A and C divided by 2 times x1, x3. Okay, now we can then use that regression equation to construct the response surface, as you can see here, and the contour plot. Okay, and you can see that we have a twisted response surface and a curved contour plot. Okay, and this signify the presence of an interaction, which of course we can see from our model. Okay, here. Now, given our results, okay, it is therefore desirable to operate at H rate close to about 900, okay, 900 angstrom per meter. And as can be seen from the contour plot, okay, there are several combinations of gap and power that enables this. No? Okay, so here. Okay, recall that the hypothesis that we are testing in the regression model is as follows. Okay, so our H naught is such that all the regression parameters are equal to each other and they are equal to 0. Okay, and then the alternative hypothesis is that at least one of these parameters is not equal to 0. Okay. And to compute for the sum of square of the model, this is just equal to the sum of square of all the factors and the interactions, okay? And this is the value for that for our example. To compute for the F naught of the model, this is equal to the mean square of the model divided by the mean square of the error term, okay? And to mean square of the model is just equal to the sum of square of the model divided by the degrees of freedom, and then we know MSE, therefore we get 32.56 here. Now, F naught is large for the model, thus we can conclude that at least one of the coefficients is not zero, okay, is not zero, which means that it is significant. Now, R squared can be computed by getting the SS model divided by SS total, okay, and that would be 0.9661, okay. R squared equal to 0.9661 indicates that about 96.61% of the variability in H rate is explained by the model, okay, and the model containing the three terms here. Now, we need to look at the adjusted R squared because the ordinary R squared always increases as more factors are included, even if these factors are not significant. The adjusted R squared can decrease if more non-significant factors are added to the model, okay? So, to compute for the adjusted R squared is just equal to 1 minus the sum of square of the error divided by the degree of freedom of the error all over the sum square of the total divided by the degree of freedom total, okay? So for our example, this would be equal to 0.9364. Okay, so it's not very different from the R squared. Now, as of course, there are several statistical packages that you can use, okay, to perform the analysis, okay, for factorial designs, okay, one of which is Design Expert, okay, and this one is an output presented in Montgomery from Design Expert for the example that we just discussed, all right? So again, as you can see here, we have the sum of square for the model, the factors, the interactions, and the error, okay? And then you have the degrees of freedom, you have the mean squares, the F value, and then the probability, the P values, all right? And we can see here again the low P values for factor A, factor C, and the interaction of factors A and C. The model also has a very low P value, which basically indicates that it is good in explaining the variability, okay, variability in the response variable, okay. And as we also computed, the R squared is 0.9661, adjusted R squared is 0.9364, okay, which means that about 96.61% of the variability in the response variable is explained by the model, okay, and at least one of the terms is significant. Of course, we found out the three are significant, all right? Okay, you can also see here the estimated coefficients and their confidence interval. Okay, so these are the final equation. This is the final equation in terms of the coded factors. All right, so the coded factors, meaning the factors take on the value of -1 to +1. And these are the final equation. This is the final equation in terms of the actual factors. Okay, so if we express the coded factors in terms of the natural levels of the factors. Okay, we also have what we call the PRESS statistic, or the prediction error sum of squares. Okay, this is basically a measure of how well the model will predict new data. Okay, and the lower PRESS, the better. Okay, so smaller PRESS indicates better prediction capability. And the sum of squared prediction errors obtained by predicting the ith data point with a model that includes all observations except the ith one is basically how you compute for the PRES. Okay, so PRES is related to prediction R squared. So prediction R squared is equal to 1 minus PRES over sum squared total. Okay. And for our example, this is equal to 0.8644. This means that the model that we derived, okay, can predict about 86% of variability in new data. Okay, so again, let's go back to this output. So you have your coefficient estimates, okay, and then you have your standard errors. Your standard error for your coefficients is computed using this formula, okay? And as you can see, the standard error is 11.87 for all the factors, okay? And this is because the design is orthogonal. Okay, to compute for the confidence interval of the coefficients, we can use this formula, okay? So, so your parameter is beta, okay? And you want your confidence interval such that you can satisfy this relationship, all right? You can see here that we are using a t-statistic at 0.025 and n minus p degrees of freedom, which means that we are looking at a significance level of 5%, okay? And you have here your standard error for your beta hat, okay? So the lower, the 5% confidence interval value would be beta hat minus this term, okay? The t-statistic times the standard error, and 95% would be beta hat plus this term here, okay? And that's how these values are computed. Now, given that we already found out that A, C, and AC are the significant terms, okay, let's look at the computer output for the reduced model. So this is the ANOVA table for the partial sum of squares, okay? And again, you can see the R squared, the adjusted R squared, and of course, all the p-values are very low, okay, because all of these are significant, okay? And you can also see here that the error, okay, the error or residual sum of squares is now composed of two. You have the pure error from the replication, okay, and the lack of fit error, which is the sum of square error of the factors that were dropped from the model, okay, the original model. Okay, so recall that for the full model, the R squared was 0.9661 compared to 0.9608 for the reduced model. Adjusted R squared was 0.9364 for the full model, and for the adjusted model, it's actually 0.9509, which is higher. And looking at the prediction R squared, okay, for the full model, you have 0.8644, whereas for the reduced model, you have 0.9302. And this signifies that the reduced model is actually a more effective predictor of new data. Okay, and therefore, the final equation in terms of the coded factors is as such. And then the final equation in terms of the actual factors is as such. Again, you have to always perform model adequacy checking. Okay, so these are the residuals. Okay, of course, there are other methods for judging the significance of effects. Okay, one is the standard error of the effects. Next, you have confidence interval of the effects, and then you have your normal probability plots.